Three of the biggest AI models in the world all advertise the same number: 1 million tokens of context. That's roughly 750,000 words. An entire code base, a full novel, months of chat history, all in a single prompt. So someone tested them. They stuffed 1 million tokens in, hit a few facts somewhere in the middle, and asked the model to retrieve them. Claude Opus 4.6 held up at 76%. GPT 5.4 dropped to 36. Gemini 3.1 Pro fell all the way to 26. The number on the box is not what the model can actually use. Most of them effectively top out around 256,000 tokens. After that, they start forgetting. Attention thins out. Information gets buried. The model still answers, it just answers wrong. So when a model claims 1 million token context, the right question is, can it actually read that many? Because mostly, no, it can't. Then on April 24th, 2026, a Chinese lab called DeepSeek shipped DeepSeek-V4. Open weights, fully downloadable, and it does something none of the other models do. It actually works at 1 million tokens. To understand why long context breaks, you have to understand what attention actually is. The mechanism is simpler than it sounds. For every token in your prompt, the model builds 3 little vectors: a query, a key, and a value. The query is what this token is asking. The key is what this token is offering. The value is what this token actually contains. To figure out which other tokens matter, the model takes one token's query and dot products it against every other token's key. High dot product means strong match. Those scores get squashed through a softmax into weights, and the model takes a weighted average of all the values. That weighted average is what gets passed up to the next layer. So attention is just lookup. Every token asks, who in this sequence is relevant to me? And the answer comes from comparing every query to every key. Now here's the part that matters for long context. When the model generates new tokens, it produces them one at a time, and each new token has to attend back to every previous one. So the model doesn't recompute keys and values from scratch every step. It caches them. That cache is called the KV cache. It's the model's entire working memory of every token it has already seen, sitting in GPU memory, ready to be looked up again on every single new token. That mechanism works beautifully at 1,000 tokens. At 1 million, it falls apart in 3 different ways. The first wall is compute. The query key dot product has to happen for every pair of tokens. With 1,000 tokens, that's 1 million dot products. With 1 million tokens, it's 1 trillion. Per layer, per attention head. Most large models have dozens of both. Even on top-end GPU chips, this takes minutes, not milliseconds. The second wall is cache size. Every token's key and value vector gets stored. Multiply by the number of layers, multiply by the hidden dimension, and at 1 million tokens, you're looking at tens to hundreds of gigabytes. That cache has to live in fast GPU memory. Most GPU chips have 80 gigabytes total. The cache is bigger than the chip can hold. The third wall is bandwidth. Even if the cache somehow fits, generating one new token means reading the entire cache from memory. If your cache is 200 gigabytes, you're reading 200 gigabytes through your memory bus to produce a single token. Even the fastest hardware crawls. And there's a softer problem on top of all this. Softmax. When attention scores get squashed across 1 million tokens, the relevant ones get tiny weights. The signal drowns in noise. The model technically attends to everything, but effectively attends to nothing. DeepSeek's answer is not to make attention faster. It's to change what attention is. V4 ships with 2 new attention layers used together. They have technical names, but the ideas are simple. The first one is called compressed sparse attention. The second is heavily compressed attention. They do almost opposite things, and the model alternates between them. Start with the first one. Compressed sparse attention. Imagine the full prompt is 1 million tokens long. Instead of comparing every token to every other token, the model first squashes groups of 4 tokens into one. So the sequence shrinks from 1 million to 250,000. Then for each token, the model only looks at about 500 of the most relevant compressed groups. Not all of them, just the top matches. The result is sharp, focused attention, but on a much smaller set. Now the second one, heavily compressed attention. Same prompt, but this time the model squashes groups of 128 tokens into one. The sequence collapses from 1,000,000 down to about 8,000. And then attention is dense, not sparse. Every token compares itself to all 8,000 compressed groups. The result is a blurry, low-resolution view of the entire prompt at once. You lose detail, but you see everything. Used alone, neither is great. Sparse attention misses the big picture. Heavily compressed attention misses fine detail. So V4 interleaves them. The first two layers are both heavily compressed, building a coarse global view of the entire prompt. After that, the model alternates, sparse and sharp on one layer, dense and blurry on the next, up the rest of the stack. Each layer covers what the previous one misses. The whole prompt gets seen, in detail where it matters and in summary where it doesn't. Here's what that interleaving actually saves. Compared to DeepSeek's previous model, V3.2, the new attention uses 10% of the KV cache and 27% of the compute at 1,000,000 tokens. That's not a small optimization. That's an order of magnitude less memory. The model fits on real hardware at full context length. No swapping, no skipping, no silent forgetting. And the recall actually holds. On the same retrieval test from before, V4 scores 0.59 at a full 1,000,000 tokens. That's not the highest. Claude Opus 4.6 still wins at 0.76, but every other open-weight model either caps out around 250,000 tokens or claims 1,000,000 and collapses long before it gets there. The closed 1,000,000 token models mostly collapse too. V4 is the only model you can download and run yourself that actually works at the full window. Cost is where this gets really uncomfortable for the closed labs. DeepSeek's smaller V4 model, called Flash, costs 14 cents per million input tokens on their API, 28 cents for output. Gemini 3.1 Pro charges $4 input, $18 output above 200,000 tokens. GPT 5.4 jumps to $5 input above its long context tier, so running a real 1,000,000 token prompt is somewhere between 30 and 80 times cheaper on V4. And because the weights are open, you don't have to use the API at all. You can download V4 and run it on your own hardware and process unlimited 1,000,000 token prompts for the cost of electricity. A full codebase analysis, an entire Slack history, a novel-length document with cross-references. None of that was economically viable on open weights before V4. Now it is. But V4 is not the best model in the world. On pure reasoning, on dense knowledge, on math, it still trails the frontier closed models by roughly 3 to 6 months. 90% on GPQA Diamond against 94 for Opus 4.7. Close, but not ahead. Opus 4.6 still wins on long context recall. V.4 does not have vision yet. It cannot look at images. So if you're picking a model for the hardest possible thinking task, V.4 is not the answer. But on coding, V.4 wins. Codeforce's rating 3206, ahead of GPT 5.4 and Gemini 3.1 Pro. Live Code Bench, 93.5%, top of the class for an open weights model. What V4 does is something different. It's the first model where you can actually use 1,000,000 tokens on hardware you control for almost no money. The closed labs were quietly charging a premium for a feature that mostly didn't work. DeepSeek just shipped a feature that does work, gave it away, and made it the new floor.